Okay, good morning, good afternoon, good evening. Welcome back to our today's lesson. So today I'm focusing on irrational values, or maybe irrational numbers. In the previous lesson we were talking about rational numbers, where we are simply saying that rational numbers are numbers which can be expressed in the form of A over B. So to recap on what we said on rational numbers this side, we said that rational numbers, these are numbers that can be expressed in the form A over B, where A and B should be the members of the integer set and B should not be 0. So any number in that form, we said that that is a rational number. So something which is irrational is basically the opposite of what we mentioned on rational numbers. So what are irrational numbers? It's the opposite definition. So the irrational numbers, we are simply saying numbers that cannot be expressed in the form A over B. So these ones, they cannot be expressed. This one can be expressed in the form of A over B, where A and B obviously should be members of the integer set and B should not be 0. So number that cannot be expressed in the form of A over B. So any number which cannot be expressed in that form, which is difficult to be expressed in that format, is basically an irrational number. Remember the characteristic of rational number previous video, we said that these are basically what? Terminating decimals. Numbers with terminating decimals. Terminating decimals. So like 0.3, the decimals ended. 1.4, the decimals ended. 1.6, the decimals ended. Or we simply mentioned if they are not terminating, then they should be repeating. So we said the characteristic can be terminating decimals or repeating non-terminating decimals. Non-terminating decimals. For example, 0.33333, the decimal is repeating but not terminating. Or maybe 0.13333, the decimal is repeating but not terminating. So when you look at the characteristics of irrational numbers is basically the opposite of those characteristics. So what are irrational numbers? So the character of these numbers, I'm simply saying the character of these numbers, the character of these numbers are those numbers, or maybe are those decimals that are non-repeating and non-terminating. So numbers having decimals which are non-repeating or non-terminating will be basically called irrational numbers. So these examples are, for example, we can talk about something to do with the root of 2, the root of 3, the root of 5, the root of 6, maybe the root of 3 plus 1, the root of 5 plus 1, and so forth. So what am I seeing here? These numbers, for example, punch root 2, what values are you going to have? You are going to have decimal numbers which are going to be formed, but these decimal numbers will be not repeating like this case where it is 333. To the values will be changing, the decimals will be changing, at the same time they won't be ending, they'll just be continuously be moving. Same root of 3, root of 5, and so forth. So all these, all numbers which are non-terminating decimals and at the same time non-repeating decimals are basically called irrational numbers. They cannot, it is difficult to express it in the form of a over b. It will be difficult to express them in the form of a over b. So what do? We just write them the way they are in sad form in most cases. So that's what we're going to do. So now let's now look at some of the examples or questions which we are going to be looking at in MA110, especially where we talk about irrational numbers. So the only questions which will come in according to rational numbers in MA110 is basically proving that these numbers are simply irrational. So are you able to prove mathematically that these numbers are irrational? That's the only concept which you have to learn in irrational numbers in this concept. So I'm going to delete, then we can now start solving questions involving irrational numbers. So the first simple question we are going to start with is basically solving or prove that. So we'll look at the example there which says prove. Let me just demarcate my board barely as usual. So prove that root 2 is an irrational number. And I'm sure by default we know that root 2 is irrational. So this time around we want to use the mathematical concept and to prove that the root 2 we are talking about is basically irrational. Well, okay, so let's start. How do we prove that a certain number is irrational? How do we prove that a certain number is irrational? So this is how we are going to prove our solution. So every time we're trying to prove that a number is irrational, we are then going to be proving by the method of contradiction. So tell them how we are proving it. So we're going to say that we shall prove by contradiction. Just saying something of this nature tells that you have data of what you're talking about. You have data. So just saying this so you really understand that some lectures will even give you just a mark for this method to say we shall prove by contradiction. This is already a direction you've given them to say whatsoever proof is here, it is basically a proof by contradiction. Contradictions means someone like doing the opposite. So more like in that manner. So that's what we're trying to, this is what we're trying to bring into light. So proving by contradiction, if I'm proving that this is an irrational number, so the contradiction method works the opposite. So I'm proving that this is an irrational number. So what am I going to do? Assume root 2 is a rational number. So the contradiction method works the opposite direction. I'm proving irrational, but this time around I'm going to assume that this root 2 is rational. So this is basically an assumption. So if root 2 is an irrational number, we know what a rational number is. From the definition, it should be expressed in the form of a over b, isn't it? So tell them, assume that root 2 is rational, then it can be expressed in the form a over b, where a and b should be members of the integer set and b should not be 0. You tell them just from the definition of the what is of a rational number. So if something is a rational number, it can be written in the form of a over b, where a and b is a member of the integer set, b is not equal to 0. So when something is in the form of a over b, in other terms you are simply saying that and these two, a and b, they have no other common factor. That's what we mean. So if something is a rational number, it can be a form of a over b. A and b should not have any other common factor except from 1. So you also write that statement, and have no common factor, no other common factor except 1. So the only thing I need to have, any common factor between a and b, the only common factor I need to have should be a 1. Anything else, then that's a contradiction to my statement. So it means we're trying to show that it is rational, but once it is being contradicting, if once that statement contradicts with this statement, then automatically that's a contradiction of what we have simply stated. So if root 2 is rational, then a and b should not have any common divisor. Common factor, it means a number can go into a and b without leaving any remainder. So they should not have any common factor. So from this statement, what do we mean? We are simply saying that root 2 is basically equals to a over b. That's what we're trying to say. It can be expressed in the form of a over b. So just from that statement, let this be your first equation. You can label it to say this is my first equation. So number, according to radical expressions here, we can now try to delete the radical. So how do we delete the radical? By expressing to an appropriate power. So root 2, for me to delete a radical, we tell them, so okay, we'll square both sides. So squaring both sides of 1, we are going to have root 2 squared equals to a over b squared. Why am I squaring both sides? I'm trying to get rid of the radical there, which is a square, so that I can now end up having this and that can go, which will be 2 to be equals to, if I have a over b power n, this power is for the numerator and the denominator again, so this can be written as a squared over b squared. This is what I'm going to have. So we can make one variable the subject. We have a squared and b squared there, so you can decide to make a squared first or b squared first, is up to you. So in this case, I'm going to make a squared the subject. A squared, if this is over 1, when we do the bad manners of cross multiplication, a squared times 1, it is a squared, to be equals to 2 times this to be 2b squared. This is what I'm going to have. So this can be taken as my second equation. So we are simply saying that in this expression, our a squared can be equals to 2b squared. So now what does this imply? So if I have a squared equals to 2b squared, 2 times b squared, what am I seeing here? This 2b squared, obviously by default, if something is multiplying by 2, then somehow this non-can is what? It's even, isn't it? It is even. For the fact that it is 2b squared, if this is my a squared, it means that the value of a squared is basically divisible by what? By 2, for the fact that it is 2 times something, for the fact that this is an even value, it's an even number. There's a 2 which is outside here. So it means if a squared is this, the same a squared I can divide by 2 completely, because I'm seeing a 2 outside here which is multiplied by that. So once I see a common factor outside there, this implies that a squared is divisible by 2. This is what this equation 2 tells me. A squared is divisible by 2. So mathematically, it is that if a squared is divisible by 2, the way math works, if a squared is divisible by 2, also a will be divisible by what? By 2. So if a squared is divisible by 2, and a is also divisible by 2. So from this statement here, if a squared is equals to 2b squared, because of the presence of 2, this is an indication that my a squared can be divided by this 2. So if a squared is divided by 2, it means even the same a can also be divisible by what? By 2. So what from this statement where a is also divisible by 2, what can I have? You guys are following through. You can pause. My board is small, so I'll be deleting somewhere. So what do I have? I'm going to delete this part. So since a is also divisible by 2, so if a is divisible by 2, it means that thus a can be written in the form. So for me to show that a is also divisible by 2, it must be a to be equals to 2 multiplied by something. For a fact that a squared is divisible by 2 because of 2 times that, even a can also be divisible by 2. So a can be 2 multiplied by a certain something. So I can say, you can use any letter of your choice. Maybe here I use my k. So a can be now be written in the form of a equals to 2k. But basically define what this k is, where k is an integer, just like that. So that even whatever I'm doing, I'm trying to define every term. So k is also an integer here. So remember, a was an integer, b is an integer. What I've also introduced, k is also an integer here. So a can also be written in the form of 2 times k, where k is a member of the integer set. So if a is equals to 2k, so what can I have? Maybe this is my third equation. We can basically replace this in what? In equation 2. So replace, we are now going to replace a equals to 2k in equation 2. Which one is equation 2? This one. A squared equals to 2b squared, that. So upper the a, we are now putting 2k, isn't it? So I'm now going to have, which was a squared equals to 2b squared, where there is a now, it is now 2k squared to be equals to 2b squared. This is what I'm going to have. Distribute the power. The power here, since it's a product inside, this power is for 2 and this power is for k. So this is 2 squared, which is going to give me a 4, k squared, which is basically k squared, to be equals to 2b squared. We can make b squared the subject here by dividing both sides by 2. If I divide by 2 this side, divide by 2 this side, what am I going to have? I'm now going to have b squared to be equals to 2k squared. So this is what I'm going to have. I can basically call this to be my third equation. Remember, my first equation was in the rational expression. My second equation, when I made a squared the subject, after replacing a up in the 2 and in the equation 2, I now form my third equation by making b squared the subject. So now, in this, just like in the first case, we said a squared is equal to 2b squared. This implies that a squared is divisible by 2. Now I have b squared to be equal to 2k squared. What can I conclude to this? Even b squared is also divisible by what? By 2. So from equation 3, you can also delete this part. So tell them that from equation 3, we see that b squared is divisible by 2. So if b squared is divisible by 2 and also b is divisible by 2. So if b squared is divisible by 2, it implies that also b is also divisible by 2. So what am I trying to have there? So if b squared is divisible by 2, even b also has a factor of what? Of 2. Everything. So from this, remember in the first place, we saw that a was also divisible by what? By 2. So what am I seeing here? Hence, a and b. So we are seeing something common between a and b. What is that common? Hence, a and b have a common factor. A common factor of what? Of 2. At the first place we said A is divisible by 2. Now in equation 3 we are simply saying B is divisible by 2. It means we are saying something similar between A and B. What is this similar between A and B? We are saying that A is divisible by 2 and B is divisible by 2. It means that they have a common factor of what? Of 2. So if from this where we are saying that they have a common factor of 2, this now contradicts. This contradicts to our area assumption. What was the area assumption which we made? The assumption was that root 2 is rational, and if we say root 2 is rational, A and B should not have any common factor. That's what we said. But here the contradiction comes in. We have that the common factor is 2. There is something common between A and B, implying that it has contradicted what we assumed. So what is going to happen here? This contradicts our earlier assumption. Hence, root 2 is not rational. Or you can say root 2 is an irrational number. As simple as that. And you have done. You've proved your statement. So this contradicts our earlier assumption that A and B have no common factor. Therefore, by the method of contradiction, root 2 is an irrational number. And you are done. So every time we are proving irrational numbers, what do? We prove by the method of contradiction, where we assume that that number is rational, and then we try to simplify and contradict to our assumption. Let's look at the second aspect. The same similar question, but a little bit different this time around. The same question, but this time around, we're now going to use root 3. So prove that root 3 is an irrational number. So it's the same process, the same method, the same steps to follow. So if you've been following throughout when we're doing root 2, the same process. The only thing which has changed there is the what? It's the 3. The same steps, the same process. The only thing which has changed is this 3. So let's now try to work out that. So we start. First step is we shall prove by contradiction. Method of contradiction. So the method of contradiction works by first assuming. So assuming that root 3 is rational, then root 3 can be expressed in the form A over B, where A and B are the members of the integer set, and A and B should not have a common factor. Should not have a common factor. So that's the assumption. So since it is rational, what are we going to go to the next step? We simply say root 3 should be equals to A over B. And this will be taken as our first equation. So from our first equation, what do? Square both sides. So square both sides of the equation. What am I going to have? Root 3 squared A over B squared. So that this and that goes, I'll remain with the 3 to be equals to A squared over B squared. So if I'm going to have that, I can make 1 the subject between A squared and B squared. This is over 1. And I cross multiply from there. I'm going to have A squared to be equals to 3 b squared, and this can be my second equation. So from our first equation, we tell them, say, from equation 2, we see that a squared is divisible by 3, this 3, and also a will be divisible by what? By 3. So if a squared is divisible by 3, implies that even the a will also be divisible by 3. So from this concept, or from this statement, we can now come up with what? An expression for what? For a. So thus a can be written in the form of what? 3k, because a is divisible by 3, so we can write the statement a equals to 3k, where k should be a member of the integer set. So replace a in the what? In the second equation. Replace a equals to 3k in equation 2. So what am I going to have after replacing a equals to 3k in equation 2? I'm going to have something of this nature now. I'm now going to have upper the 8 is 3k. So if we had a squared equals to 3b squared, upper the 8 is now 3k squared to be equals to 3b squared. This square is for 3 and this square is for k. So 3 squared, I'm going to have 9. K squared, I'm going to have k squared to be equals to 3b squared. Make b squared the subject, divided by 3, divided by 3, this goes, and the b squared will be equals to 3 into 9, that's a 3k. This is my third equation. So from the third equation, what am I saying? B squared is equals to 3k. So from equation 3, we see that b squared is divisible by 3. Hence, also b is also divisible by what? By 3. So from this statement, we can see some similarities between a and b. We can now see some certain similarities between what? A and b. So by simply saying that thus A and B have a common factor of 3, which contradicts to our area assumption. Our area assumption that root 3 is rational. Therefore, root 3 is irrational by contradiction. And you are done. So, same process. Even if it was root 5, same process. Root 6 will do the same process. Now, look at something which is a little bit complex, but it's basically the same. So, this question is going to be as follows. So you can pause and you can be following through. So this time around now we're trying to prove something a little bit twisted but known, where we're simply saying prove that, trying to divide my board per minute, prove that 1 minus root 3 is irrational. So this is a little bit combined. 1 minus root 3 is irrational. So how do I prove that 1 minus root 3 is irrational? Same process, same steps, same procedure. So we're simply saying we shall prove by contradiction. So by proving by contradiction, what do we do? Assuming 1 minus root 3 is rational. Assuming that 1 minus root 3 is rational and it can be expressed in the form a over b, where a and b should be the members of the integer set and what have no common factor. So this is the assumption which we have made. So what is the next part now? So after making that assumption, you tell them 1 minus root 3 should be equals to what? A over what? B. That's a rational number. So next, I'm trying to make root 3 number the subject. So I'm going to have negative root 3 can be equals to A over B. When this one crosses, actually the best would have just been so I have 1 minus root 3 equals to A over B. Make the radical the subject. So this one can cross the other side, becomes 1 minus A over B to be equals to positive root 3. This is what I'm going to have. So implies that root 3 is basically equals to 1 minus A over what? A over B. This is what we have there. So if I try to simplify that as a single fraction, this is over 1. So root 3 can be taken as the lowest common denominator between b and 1 will be basically b. 1 into b is b. B times 1 is b. B into b is 1. 1 times that is minus a. This is what I'm going to have. And then from there, what am I going to have? I'm now going to have the same root 3 as expression b minus a over b, which is my equation there. So root 3 equals to b minus a over b. What can we state from statement 1? So if a is an integer and b is also an integer, this implies that b minus a can also, the outcome of b minus a is going to also be what? An integer. So from statement 1 here, from statement 1, we see that b minus a is an integer and the same b in the denominator is an integer. So if b minus a is an integer and the b also in the denominator is an integer as a fraction, then this contradicts to something. So when proving that such a combined expression is irrational value, meaning that you have to have already the knowledge of root 3. So sometimes they will tell you to say, with the concept that root 3 is irrational, prove that this is also irrational. So we've already proven that root 3 is irrational number. So b minus a over b is something telling us that root 3 should be rational, and that should not be this case. So since b minus a is an integer and we see that b in the denominator is also what? An integer. So what are we simply saying? What are we simply saying? And since we know that root 3 is irrational, so root 3 we already know the concept that is irrational, then statement 1 contradicts contradicts that this is a what? Irrational number. So then statement 1 contradicts, because you tell them, say, because rational cannot be equal to a rational number. So root 3 is already irrational. Then this statement 1 is now contradicting us something, because this is an integer over an integer telling us that root 3 is irrational. But we know that root 3 is irrational already from previous proofs. So this contradicts, because rational cannot be equal to an irrational number. So from this statement now tell them, say, hence 1 minus root 3 is also what? Irrational. Done deal. Series. So any question which involves irrational numbers, proving that irrational numbers, basically what method are we using? We are using the method of contradiction. We'll be using the method of contradiction. So exercise which you can basically submit in our inbox is as follows. So the exercise which you can work with is as follows. So work with, the question is prove, or maybe I'll say given that root 3 and root 5 is irrational numbers, are irrational. So given that root 3 and root 5 are irrational, show that the following are also not rational numbers. So we want you to show that the following are not rational numbers. So the following are: number 1, so show that root 3 plus 5 is an irrational number. From the knowledge that root 3 and root 5 are already irrational. The same process. This was the one which of just from solving was 1 minus root 3. Now this time I see root 3 plus 5. The same steps, the same process, you'll be able to be replacing just there and there. The only difference here is root 3 plus 5. So where there was 1, it is now plus 5. Number 2, show that root 5 minus 1 is also an irrational number. The same steps and the same process. Number 3, show that 1 minus root 3, actually we've already solved this one, is an irrational number as well. And so forth. So this is your task. You can send in our inbox 0964736805. Thank you very much and have a blessed. Yeah.